Good morning, class. Today we're going to continue on with Chapter 3, Section 1. So remember, this section is all about using and expressing measurements. So here is our opening slide. You can easily read the temperature on a thermometer to the nearest degree. So for example, on this thermometer, I can see that it's reached up to 20, and I can look at these tick marks and read exactly which degree it went up to. You can also estimate the temperature to about the nearest 10th degree by noting the closeness of the liquid inside the calibration. So let's actually break that down. So for example, what I mean by estimate is these tick marks go up by 1 each time. So 21, 22, 23, 24, 25, 26, 27, and so on. Now, if there is, for some reason, it's between 2 tick marks, that is where that estimated number comes in. So suppose right now I can see that here's my 20 mark. So I can see it's at 21, 22, and it's almost at 23, but not quite there. I can estimate that it's at 22.9 degrees Celsius. So this estimated number of 22.9 degrees Celsius actually has 3 digits. The first 2 digits, the 2 and the 2, are known with certainty. I know that it's above the 20, and I know it's above that 22 mark. Now that rightmost digit, this 9 right here, it was estimated. I don't know if it was exactly 0.9, maybe it was 0.8. So there is that uncertainty of that measurement. So these reported digits, they all contain useful information. And we're going to learn that these digits are called significant figures, or I'll call them sig figs. So what is a sig fig? Well, a sig fig in a measurement is the digits that are known, like we saw with the temperature, and the last one that is generally estimated. So why must measurements be reported to the correct number of sig figs? Why do we have to learn them? What is their importance? Well, measurements always have to be reported to the correct number of sig figs. And the reason is because calculated answers depend on the number of sig figs and the value. For example, you can never have more sig figs than the lowest measurement will allow. So instruments differ in the number of sig figs that can be obtained from their use, and thus the precision of measurement. So for example, right here we have 3 different meter sticks. The first meter stick is calibrated to be 1 after the decimal. So if I have a measurement here, I can say, okay, well, maybe that's about 0.8 of a meter. The second meter stick gives me a more precise measurement because I can get 2 after the decimal. So here I know for a fact it's 70, but right here I'm going to guess 77.77. And the third meter stick is even more precise and gives me 3 numbers after the decimal. And here I can say 70. Well, I know it's 0.77, and my estimated digit is that 2. So all of these give different number of sig figs. For example, this one has 1, this one has 2, and this one has 3. So there are 3 different tools, so that's what it means by instruments differ in how much they can have. So the more precise the tool, the more sig figs you're going to have. So determining sig figs is what we're going to do today, and then tomorrow we're going to learn how to calculate with them. Because in order to calculate, you're going to have to know how to find them, and so that's why we're going to spend an entire day on it. So determine whether a digit is in a measured value is significant. There are rules that you're going to have to follow. If you are uncertain if a 0 should count or if a number should count, go back through these rules step by step. So the first rule is every non-zero digit in a reported measurement is assumed to be significant. So any number like 1, 2, 3, 4, 5, 6, 7, 8, 9 are all significant. So here, non-zero, 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 this has 3 sig figs. Same thing down here, 1, 2, 3, 3 sig figs. 1, 2, 3. 3 sig figs in this one as well. The second rule, and this is where people start to get confused, is with zeros. So the following rules are all going to be about zeros. Zeros appearing between non-zero digits are significant. So for example, these zeros are between 7 and 3, so they count. So this has 4 sig figs. This 0, again, is between the non-zero digit 4 and 7, so it counts. So I have 4 sig figs there. This 0 is between the 5 and the 3, so yes, it also counts. And so this is also considered significant. So again, between non-zero digits are significant. Yes, they count. The third rule, the leftmost zeros appearing in front of non-zero digits are not significant. I often call them leading zeros because they're in the front. It doesn't matter where the decimal place is at all. If they're in the front, they're acting as placeholders. So when we actually write things in scientific notation, most of you guys realize that you can just get rid of those beginning zeros, and that's because they are insignificant. So for example, here, these 3 zeros come before the first non-zero digit, so they do not count. So right here, I have 2 sig figs. Same thing with here. This 0 comes in front because here's my first non-zero digit. So there are 2 sig figs here as well. And then lastly, here's my first non-zero digit. So everything in front of it, all those zeros in front of it, does not count. I have 1, 2 sig figs again. Okay. And the fourth rule is zeros at the end of a number. I like to call them trailing zeros because they're at the end. And, so here's the big kicker, and part of a decimal are always significant. So you have to have that decimal in order for it to count. So here the zeros are at the end, and I see this decimal here, so I have 4 sig figs. Here, this 0 counts because it's between 2 non-zero digits, and then this one also counts because I have a decimal. And then lastly, this one also has 4 sig figs because although these zeros are at the end, I have a decimal here that makes them significant. But what if they come at the end and there is no decimal? So zeros at the rightmost end, or those trailing zeros that are not part of a decimal, are not significant. They act as placeholders. So for example, these zeros are at the end, but there's no decimal anywhere in this number. So this 0 and this 0 cannot count, and I only have 1 sig fig. Here, I have zeros at the end, so I have to look for a decimal, and I don't see one. So these zeros cannot count, so I still only have 1 sig fig. And lastly, this 0 also is at the end. I don't see any decimal in this number whatsoever, so this one cannot count. So 1, 2, 3, 4. This has 4 sig figs. Now there are 2 situations in which numbers are going to have an unlimited number of sig figs. The first one is if you're counting, because when you count something, it's known as an exact number. So if I were to measure 23 people in the classroom and I counted 23 people, that is considered unlimited sig figs. The second situation is those in which you call conversion factors. So these are defined quantities as found within a system of measurement. So conversion factors, what they are, and we're going to learn about them in more detail coming up, is they mean the same amount, they just have different units. So 60 minutes, if I say 60 minutes, it equals 1 hour. 100 centimeters equals 1 meter. So those will not count in any kind of measurement either. So let's do some practice problems. So what I want you to first do is pause this video and see if you can figure out how many sig figs these numbers have. So make sure you understand the rules for counting sig figs before you begin. So if you need to go review them, please review them, and then we'll go over the answers. Okay, let's look at the answers. So letter A, this is a non-zero digit, so it's okay. Non-zero digit, so it's okay. And then non-zero digits also count. So this has 3 sig figs. If I were to look on this, all non-zero digits count. So we already know the 4, 5, and 6 count. But now I need to look at those zeros. The first rule says zeros between non-zero digits count. So since this is between the 4 and the 5, we're good. Since this is between the 5 and the 6, also good. So this one has 5 sig figs. Now to go to letter C. Here, non-zero digits count, so these ones automatically count. And then we look at these zeros here. Well, they're not between non-zero digits, so we got to move on to our next rule with zeros. And I see that they're not leading zeros because they're not in front, so I don't have to worry about that. And I go to my next rule, and these are trailing zeros. So since these are trailing, I have to look for a decimal, and here's the decimal. Since I see it, these count. So this letter C also has 5 sig figs. Now letter D, you can argue if she counted 22 meter sticks, if she counted it, it's unlimited. But if she didn't count it, we could also say that it has 2 sig figs. Letter E, non-zero digits count automatically. So let's go to our next rule. Zeros between non-zero digits count. So here's a 0, and it's between the 7 and the 8, so it counts. The rule after that says leading zeros never count. So for example, this 0 and this 0 will not count since it's in front. And then our last 2 rules end with trailing zeros. So zeros at the end, they only count if there is a decimal. So here, I see a decimal, so this one counts. This has 4 sig figs. And letter F, non-zero digits count. So then the zeros are not between non-zero digits, so that rule doesn't apply. They're not leading zeros, so that rule does not apply either. So these are trailing zeros. So for trailing zeros, I have to look for a decimal, and I don't see any. So since they're trailing with no decimal, these cannot count. So this only has 2 sig figs. So let me actually know how you did. If you struggled with those, make sure that you shoot me an email. We can set up a meeting and actually go through this a little bit more in detail with some more examples that you and I walk through. However, if you don't have any issues, you can go ahead and start the homework assignment found on the classroom website. I hope you have a good day. Bye.